So consider the following. Consider the following. Let's see. X plus 3 quantity squared. And how about x minus 5 quantity squared? All right. All right, what is a good step to go about expanding those binomial squared?
X plus 3 times x plus 3.
Okay, so how about writing this as an x plus 3 times itself, right? Because that's what this power indicates. Every time we have a power, that indicates that we are supposed to multiply whatever quantity with itself as many times as we see in the exponent. And well, from here, any ideas what to do next from here? Foil. All right, so let's go about foiling here. Okay, so x times x times 3, that's going to give us x squared plus 3x, and then what's then going to be? So that's going to be 3 times x and 3 times 3. That'll be 3x and 9. And combining these together, well, we get x squared plus 6x plus 9. All right. So that's final answer for the first example. Let's how about we do the same for the second one? X minus 5 times itself. So let's see. X minus 5 times itself, x minus 5. And we're going to take the same approach about foiling, that is x times x, and take x times negative 5. That is x squared minus 5x, and then negative 5x and plus 25. So another minus 5x and a 25. All right. Now, combining like terms, x squared minus 10x plus 25. All right. The middle term is twice the product of the terms in parentheses from the original exercise. From the original expression. Let's call it expression instead. All right. And again, okay, let's see. Okay, what about x times 5? What is that? X times 5?
5x.
5x. Multiply that by 2. Isn't that same 10x right here? Whether it's positive or negative, that doesn't matter. What about that x plus 3? What about x times 3? What is that? Times 2? Isn't that the same 6x? Well, in this case positive, in this case it's negative. So if we have a positive in between, well, all terms are positive. If we have a negative in between, this will be negative for that middle term. Now, can we generalize this? Well, just so we can go a little deeper into this. Okay, I'm not going to use x and numbers this time. I'm just going to use the quantity a. Okay, hold on. Let me change colors. I'm going to go a plus b quantity squared. Just in general, no x's, no numbers. I'm just going to use letters a and b. Okay, the same way, this is a binomial squared. That square indicates that we multiply a plus b, and quantity times multiply the same quantity a plus b. And how about we FOIL? So a times a a times b. And that's going to be a squared plus ab, and then b times a, b times b. But the product b times a can be rewritten as a times b. I mean, we can go in alphabetic order instead. And also that works because the product is commutative. A times b is the same as b times a. So that's another a plus a times b. And lastly, plus b squared. All right? And combining these two together, a squared plus 2ab plus b squared. All right? And I think this generalizes in a more symbolic way all these ideas we wrote in red at the top of the page. So the first and the last term, and the first and the third terms are perfect squares, and the term in the middle is the product of the first two terms the product of the two terms in the parentheses times 2. It should work the same way if we go a minus b instead, squared, but that's just going to change a squared plus a minus 2ab plus b squared. All right? Or if you want a more condensed way, you can use the plus minus notation. A plus minus b squared equals to a squared plus minus 2ab plus b squared. Well, when is it going to be a plus right here? When you have a plus. When is it going to be a minus? When you have a minus here. All right? So, that's a more generalized way to talk about perfect square trinomials now. For instance, we can use this formula right here, well, or this idea, to expand other kinds of binomials like x plus 64, not 64, minus 7 squared. Right, we can do the same. How about we just square the first term, that's x squared, multiply x times 7, which is 7x, but that times 2, isn't that 14x? But in this case, minus because we have a minus here, and plus 7 squared, which is 49. Right? Rather than doing the foiling. However, if you want to do the foiling, that's up to you. That's fine. That's acceptable. However, the reason why we need to understand this pattern recognition, it's because when we do this factorization of perfect square trinomials backwards, you'll see how is that going to play out in the end. Let me do one more. How about what's that? 3x plus 4. All right, now we're adding a coefficient to the first term, okay? But it works the same, and we need to be careful here. What do we get when we square the 3x? 3x squared? 9x squared. Be sure to also square the coefficient, not just the variable. So that's a 9x squared. Okay, what is 4 quantity squared? 16. Okay, so 16, let me put it at the very end. And now let's multiply 3x times 4. What is that? 12x, but in this case, remember we multiplied that by 2? That's going to give us 24x. All right? And of course, again, you have the other alternative, FOIL. But again, I need you guys to see this idea of how squaring a binomial gives us a perfect square trinomial, what we call a perfect square trinomial, because now we are going to factor these perfect square trinomials. Number one, first of all, we need to check whether a given trinomial is one of those perfect square trinomials in order to use the method we're going to do. Otherwise, if it's not, well, then we will have to go with another alternative. All right? Now let's see. Okay, now let's go back to the page 7. So I mean, some of you just flip the page. Okay. Factor perfect square trinomials. Now we're going to see this backwards. This formula, do you see this? Do you recognize these two from the back side of the page? Well, they're now backwards because now we're going to start with a polynomial and we're going to turn this into products of a binomial square rather. And well, again, a pattern to notice about these trinomials above is, remember how we found out that the first and the third term are perfect squares? All right, and twice the product of the square roots is equal to the second term. All right, so and that's how we are going to determine or rather identify this as perfect square trinomial. So this is how we perform the test, if you will. Now check this out. Number one, what quantity squared equals to x squared? X. What is that? Which one? X. Just x, right? What quantity squared equals to 25? 5. 5, all right. Did you notice how the first and the term are perfect squares? Okay, so this is what we're going to do. I'm going to multiply, so this, let me call this A, and let me call this B. All right? Let's evaluate the quantity 2AB. The quantity 2AB will be 2 times the quantity A, which is x, times the quantity B, which is 5. That will result into 10x. Now the question is, does that 10x matches with the middle term of this trinomial? Then we have a perfect square trinomial. And we can simply go about, okay, because this is simply A plus B, quantity squared. In this case, our quantity A is x, our quantity B is 5, and separated by the sign of the middle term, which is 5, and the whole quantity squared. All right? Okay, so that is if we go the if we go the perfect square trinomial approach, which is trust me, in later problem, this tool is going to be very, very powerful to save a lot of time and expedite a lot of calculations. However, this trinomial we have over here can be factored using the double bubble method, because from here, factors of 25 that add up to 10, what are those factors?
5 and 5.
5 and 5, right? X plus 5. X plus 5, and surprise, check this out. Isn't that the same as saying x plus 5 squared? Right? Either way, it's up to you. But again, this pattern recognition for perfect square trinomials will be useful more often than not. All right. Let's have a look at letter B and determine whether that given trinomial is a perfect square trinomial, and if it is, factor it using this approach we have over here. All right? Okay, so number one, let's identify the quantity A. That is the quantity whose squared equals to x squared. What is that quantity? X. What about the quantity whose squared equals to 36? 6. Okay, so far so good. All right. The first and the third term are perfect squares in accordance with the first specification here. Now let's evaluate the quantity to A, B, which in this case is 2 times the quantity x times the quantity 6. That's going to result into 12x. Now the question here is that 12, does that 12x match it with the middle term here? So this is not a perfect square trinomial. So we will not be able to factor it using this perfect square trinomial method. So we will need to look for another alternative. It looks like the double bubble method here would be a good alternative. Okay, factors of 36 that add up to 21. Is it even possible? 36 times 1, definitely not. 18 times 2, it's just 20. We're only one unit short. And then what else? 3 times 12, no, it's definitely not going to work, right? Well, It can, so it's number one, it's not even a perfect square trinomial, and on top of that can't be factor. And recall, I don't know if we mentioned this, but whenever we cannot factor a polynomial, we just call it prime. I don't think we look at this, right? No, we didn't. Just call it prime. And just as, I mean, because it's the same thing as with numbers. For instance, the number 18. No, maybe a simpler number. Well, yes, 18 is fine. That is 2 times 9, and at the same time that's 3 times 3. That means the number 18 can be written as the product 2 times 3 squared. So this, because of this reason, this number 18 is a composite number, not a prime number. On the other hand, if we try, how about 17, for instance? Can we divide 17 by 2? No, by 3. Actually, 17 is a prime number. And again, prime numbers are numbers whose factors are only 1 and themselves. All right? And in this case, well, since there was no way to factor this trinomial into a product of smaller factors, x plus 5 times x plus 5, like in letter A, well, we were not able to factor it. Well, then that means it's prime. All right? Let's see. Oh, okay. Let's look at letter C. All right. Let's find the quantities A and B. Okay, A equals, B equals. Okay, the quantity A will be that quantity whose squared equals to 4x squared. Careful with this one.
2x.
2x. Recall to raise not just the x but also the coefficient, and it looks like the 2x just works over here, right? What about 25? Is that 5? We already did that one, right? Okay, now let's evaluate the quantity 2ab. That is 2 times the quantity 2x times the quantity b, which is 5. All right, 2 times 2 equals to 4. 4 times 5, isn't that a 20? Times the x equals 20x. Now the question here, does that 20x match with the middle coefficient here? I know what you might be thinking, potentially no, that's because of the sign, but that doesn't matter. In the end, we are going to factor this guy. The quantity A, which is 2x, the quantity B, which is 5, the whole quantity squared, but in this case, split by the sign that we have for the middle term, which is, in this case, negative. Right? So again, let's find the quantities A and B. The A is going to be the quantity whose square is x squared. All right, what's that quantity? 36x squared. 6x. And what about the quantity whose squared is 81? 9. Okay, let's evaluate the quantity 2ab to determine whether this is a perfect square trinomial. All right, and well, 2 times 6, that's a 12. 12 times 9, is that 108? Okay. 108x. Compare this result with the middle coefficient. Is it the same? Well, then this is not a perfect square trinomial. All right? So, not a perfect square trinomial. All right?